All right, everyone, and welcome back to the channel. Today, we're going to take a deep dive into something that's kind of like a classic debate in electronics. Analog versus digital. And some of you out there, you might be saying, hey, come on, isn't digital like the obvious winner here? But I think by the end of this, you might find yourself thinking about this whole thing a little differently.
What's interesting about this whole analog versus digital thing is that it's not as simple as it might seem at first glance.
Yeah, that's a really good point. So let's just start with the very basic difference. We always hear analog signals are continuous and digital signals are like these discrete things.
Right.
What does that actually mean, practically speaking?
So imagine you're trying to measure the temperature of a room with an analog thermometer, like the old school mercury kind of.
Yeah.
The mercury rises smoothly and continuously as the temperature changes. Any tiny change in temperature, even a super small one, it's going to cause a change in that mercury level. And that's continuous, like the signal can take on any value within a certain range.
So it's like almost like a dimmer switch where you can adjust the brightness across a whole spectrum.
That's a perfect analogy.
Okay.
Now let's look at a digital thermometer. It's going to show you the temperature as a series of numbers. 72 degrees, 72.1 degrees, so on. It's quantized, right? So it's broken down into these steps or levels. You don't get values in between those steps.
Gotcha. So it's almost like the difference between a ramp and a staircase.
Yes.
With a ramp, you can go up and down smoothly, but with a staircase, you have to go to each step.
Precisely. And this fundamental difference between continuous and discrete is huge. It changes how analog and digital systems deal with information, noise, and precision.
Okay, so let's dig into that noise thing a little more. That seems to be a big deal in electronics.
Oh, absolutely. Noise is like the enemy of any electronic system. It's basically just unwanted disturbances in a signal, and it can really mess up the information you're trying to send.
So like static on a radio or the snow on an old TV?
Exactly. Think of it like you're having a conversation in a loud room. It's hard to hear what someone is saying with all that background noise.
Right, all that chatter.
Exactly. And here's the thing. Analog signals are way more sensitive to noise than digital ones. Any change in the signal, even a teeny tiny one, can change the information it's carrying.
So like if you write a message in ink and the paper gets wet,
Yeah.
the message gets all messed up.
That's a great way to picture it.
Okay.
And as analog signals get copied, amplified, or sent over long distances, that noise builds up and the signal degrades.
Kind of like making a photocopy of a photocopy.
Uh-huh.
And each time it gets a little more blurry, a little less clear.
Precisely. That's a big reason why analog recordings like old vinyl records or cassette tapes lose their quality over time.
Yeah.
The noise just builds up with each playback.
Right. That makes sense. But you mentioned something about analog signals failing gracefully.
Yeah.
What does that mean when we're talking about noise?
Right. So while analog signals do have a problem with noise, they tend to degrade gradually.
Okay.
Think about that old cassette tape again. You might hear some hiss and crackle, but you can still hear the music, mostly.
Okay.
The signal gets a little fuzzy, but it doesn't completely disappear. The information is still there, it just has some noise added in.
So even though the quality isn't as good, it doesn't just suddenly stop working.
Right. It's more like a gradual fade.
Okay.
Now let's think about how digital signals handle noise. Remember how we talked about digital information being quantized in those steps?
Yeah, like those stepping stones across a river.
Exactly. That's the key to how well digital signals deal with noise.
Okay.
So picture those stepping stones again, even if the river level changes a little bit. As long as you stay on the stone, you're good.
So little changes from noise don't matter too much unless they push the signal off the step.
You got it. Digital systems are made to ignore those small changes.
Okay.
And this makes digital signals super resilient.
Right.
They can be copied, sent, and processed without losing much quality at all. Think about a digital music file. You can share it, download it, play it 1,000,000 times, and it'll sound pretty much the same as the original.
Wow, that is impressive. It's like the difference between photocopying a handwritten note and copying a computer file.
Exactly.
The computer file will always stay the same no matter how many times you copy it.
You got it. But there's a catch.
Uh-oh.
While digital signals are really good at handling low levels of noise, they can fail completely if the noise gets too strong.
Really? I thought digital was supposed to be more reliable.
Well, think of a CD with a scratch on it.
Okay.
The digital data is either read correctly or it's just lost.
And you get those skips and errors.
Right, it's all or nothing. Unlike analog, which degrades over time, digital systems have a clear breaking point. Once the noise gets too strong, the information can get totally messed up.
So it's like a bridge.
Yeah,
It either stands strong or it collapses completely. There's no in between.
exactly. Great analogy.
So we have analog, which is sensitive to noise but fails gradually, and then digital, which is good with noise but can fail dramatically.
Right.
Sounds like there are trade-offs with both.
Definitely.
But what about precision? Which one wins there?
Well, both analog and digital systems have limits when it comes to precision, but they approach it in very different ways.
Okay.
With analog precision, it's limited by two main things. There's the noise in the system, like we've been talking about. It's like trying to measure a piece of string that's blowing in the wind. You'll never get a perfectly accurate measurement.
Yeah, that makes sense. What's the other thing that limits precision in analog?
The components themselves. Even the best designed analog circuits have limitations. For example, there's something called shot noise, which is caused by the random movement of electrons within a conductor. And that's just a fundamental source of noise that you can't get rid of completely.
So even if you could somehow remove all the external noise, you'd still be stuck with the limitations of the components themselves.
Exactly. It's like trying to draw a perfectly straight line, but your hand is a little shaky. It's never going to be perfect.
Okay, I get it. Now, let's talk about how precision works in digital.
All right, so in digital, we're dealing with bits, ones, and zeros. Precision here is all about how many bits are used to represent the information. Think about pixels in an image. More pixels means a sharper, more detailed picture.
So more bits equals more precision.
Exactly. Every extra bit doubles the number of levels that can be represented.
Right, so you can make finer distinctions.
Right, but there's a limit, of course.
Okay, what's the limiting factor?
The main limitation is the performance of the analog to digital converter, or ADC. That's the thing that translates real-world analog signals into digital.
Right, because even in a digital system, you still have to interact with those continuous analog signals.
Exactly. The ADC basically takes snapshots of the analog signal at regular intervals and gives each snapshot a digital value based on how strong it is. And the more bits the ADC has, the more accurately it can represent those analog values.
So a good ADC is key to having high precision in digital systems.
You got it.
Okay.
But don't forget about the digital to analog converter. Does the opposite. It converts digital signals back to analog.
Right, because at the end of the day, we experience things in the analog world.
Right.
Whether it's listening to music or seeing the brightness of a light bulb.
Exactly. So you have this constant back and forth between analog and digital.
Right.
With ADCs acting as the translators.
Okay, this is starting to make a lot of sense. We've gone from the flow of analog signals to the precision of digital, and we've seen how each has its pros and cons.
Yeah.
But you said earlier that designing analog circuits can be tricky.
It can.
What makes it so hard?
Well, analog design is often called more of an art than a science.
Oh, really?
Yeah, it takes a deep understanding of how circuits work, a knack for picturing how signals move through components, and a lot of intuition that comes with experience. It's not just about connecting parts together. Analog circuits can be really complex and sensitive. You have to think about things like how much the components vary, temperature changes, and even weird side effects that can mess things up.
So it's a really delicate process.
It is. In contrast, digital design is usually more straightforward. With digital, you're working with ones and zeros, which makes things a lot simpler.
Gotcha. So it's more like working with a set of building blocks, like putting together a puzzle.
Exactly. And because digital systems are so well-defined and standardized, a lot of the design process can be done automatically with software tools.
That sounds way easier.
It is.
No wonder digital has become so popular. But if digital design is generally easier and more precise, why even bother with analog anymore?
That's the big question. The answer is that we can't live without analog. The physical world we interact with is analog. Light, sound, temperature, pressure, all these things are continuous analog signals.
So even though our computers and phones are digital, they still need to be able to talk to the analog world.
Exactly. Think about your smartphone.
Okay.
It's full of digital processors and memory chips, but it needs analog components to work. The microphone, which turns your voice into electrical signals, the touch screen that knows where your finger is, and even the wireless receiver needs analog circuits to amplify and filter the radio waves.
Wow. I never thought about how much analog is inside our digital devices.
It's everywhere. Even a simple digital clock needs an analog oscillator to create the timing signals for the digital parts.
So it's not really analog versus digital. It's more about understanding that both are important and work together in modern electronics.
Absolutely.
And it brings up another interesting point. We talked about how analog design takes special skills and a bit of an artistic touch, while digital design is more about automation and following standards.
Yeah, and that difference has really changed how electronics have developed over time. Digital design is relatively easy and affordable, and that's led to the huge growth of digital technology.
Right, smaller devices, more software applications. It's like comparing handcrafted furniture to mass-produced stuff.
Yeah.
Both have their place, but mass production makes things accessible to a lot more people.
Exactly, but that doesn't mean analog design is going away. It's still really important for things like high-quality audio equipment and advanced medical imaging systems.
So as digital technology gets better, the need for skilled analog designers will only increase.
I think so, yeah.
It's like this hidden profession that's essential for the digital age.
It is.
That's a really good point. So before we wrap up, I want to leave our viewers with a little challenge.
Okay.
As you go through your day, take a look around at all the electronics you use.
Your phones, your laptops, your cars, even your kitchen appliances.
They all rely on this balance between analog and digital electronics.
It's true.
See if you can figure out which parts are analog and which parts are digital.
That's a fun way to learn more about the technology that surrounds us.
Yeah, and to appreciate how these two fundamental approaches work together. We are AI experts.
Please subscribe, like, and leave your thoughts in the comments below.
Thanks for watching.